We're glad to see everybody who's in attendance, and it looks like our numbers keep climbing up, so we're real excited about that. I'm excited today about the panel of presenters that we have. These three gentlemen are going to bring a perspective to the table about where the needs are within the nuclear industry supply chain for their respective projects. And they're going to outline for us where the known gaps are and then where maybe the unknowns are also out there, so that businesses can get an idea of where the potential future business may lie. So with that, I'm going to do a quick round of introductions, a little bit of housekeeping first. We would really like you to engage with us. So if you have a question for one of the presenters, just drop it in that questions tab on your webinar control box, and we will answer those questions at the end. So we look forward to that engagement at the end. So with that, I'm going to introduce our three presenters, and then Nick will kick it off when we're done. So Nick Smith is our Deputy Director for the National Reactor Innovation Center here at the lab. In this role, he is responsible for supporting initiatives to provide resources to reactor innovators to test, demonstrate, and conduct performance assessments to accelerate the deployment of advanced nuclear technology concepts. So thanks, Nick, and welcome. Dr. Corey McDaniel leads the implementation of the lab-wide commercial business development strategy here at the lab, and he's our Director of Industry Engagement and our Chief Commercial Officer. So thank you, Corey, for being with us today. And then we have Lee Nelson, our final presenter, and Lee is the Director of Procurements and Logistics for the Versatile Test Reactor Project. In this role, Lee is establishing the subcontracts needed to support the VTR, as well as establish the digital engineering tools that are going to be needed to design and build the VTR. So with that, Nick, I'm going to kick it over to you. And again, thank you everyone for being here.
So, can everybody see me, hear me?
We can.
And is my screen showing up now?
There's your slides, yep.
Okay, good deal. So, appreciate the opportunity to present today. I wanted to run through a little bit about what NRIC is working on and what this new program is all about. So, a lot of you may be familiar with INL's history as the National Reactor Testing Station. So between 1949 and I think 1974, there were 52 different reactors that were built on the INL site. And that's really the foundation that the existing commercial nuclear fleet is built off of. It started with the nuclear navy and the submarine reactor tests, and has continued into the reactors that we know today, like ATR, and TREAT, and NRAD. NRIC, or the National Reactor Innovation Center, is a new DOE program that was authorized by the Nuclear Energy Innovation Capabilities Act. And really our single objective is to enable new nuclear reactor demonstrations, experimental reactors. And we are doing that by establishing trust and predictable collaboration with industry partners, trying to really understand the details of what industry needs to enable their experimental reactors and what their development challenges are. And then also by creating infrastructure and capabilities that multiple reactor designers need to increase the technology development on their reactor designs. So NRIC is a little bit different than a traditional DOE NE program in that we're not solving general topic area problems in a scientific space, but we are targeting the specific problems of reactor designers in the context of trying to get that experimental reactor built. So there's a lot of exciting opportunities coming up and that have recently been announced. Some of you may have been following the DEFOA 2271, which is the Advanced Reactor Demonstration FOA that DOE put out this summer. That FOA had 3 separate award pathways. The largest awards were called the demo awards, and those were announced a little bit over a month ago, maybe. But TerraPower's Natrium concept and X Energy's XE100 were recently selected for award there. And these are awards that are intended to be between $400 million and $4 billion across 7 years to build demonstrations of these reactor concepts. The next tier for the awards was the risk reduction pathway, and those are anticipated to be announced any day now. DOE has been telegraphing that they have that information ready, that the awardees are selected, and so they're in the final stages of preparing to announce those awardees. So look for that news coming up any day now. And then there's a third pathway, the Advanced Reactor Concepts 2020, which is smaller than the risk reduction awards, and it's intended to enable concepts that are a little bit lower technology readiness level or that need some more development before they're ready to explore building an experimental reactor or demonstrating. So NRIC worked in coordination with INL on responses for 18 different potential projects, and there will be somewhere between 5 and 9 awardees by the time this is all said and done. So I guess 6 and 9 would be the minimum. There's also the Office of OSD, Office of Security and Defense, I think it's DOD, and their Strategic Capabilities Office had a request for solutions for the mobile nuclear reactor. They're calling it the Pele program. And this one was announced, the awardees were announced earlier this year. BWXT, Westinghouse, and X Energy, all three are selected and have been working on mobile nuclear reactor designs that would utilize TRISO fuel in a Connex box-mounted reactor. They've got constraints about being able to carry the reactor in a C-17, which puts requirements on the total weight. But this is another exciting opportunity, and NRIC is trying to be prepared for potentially hosting those demonstrations in a project that we're calling the Irig Dome, which I'm going to talk about shortly. So with the objective of enabling experimental reactors, we started thinking about how we would do that. And what you're looking at here is kind of a high-level overview of a demonstration reactor test bed. So the systems in blue would be permanent systems that multiple users would take advantage of to demonstrate their reactor concept. The systems in green would be temporary, and they would be brought in by an industry partner, connected to the test bed, operated for something like 6 months, and then that reactor would come out of the test bed and a new reactor could come in. So it really takes advantage of that investment infrastructure and allows it to be a benefit to multiple concepts and creates that pipeline of advanced reactor designs that are kind of getting their scale-up testing in before going on to, a commercial application on some other site. The first project I'd like to talk about is the Irig Dome. And so this is the project to modify the EBR2 dome at MFC, but make it compatible with this testbed philosophy. So there's things that need to be done, like expanding the door to get equipment in and out of the dome. You can see there's a closed loop Dowtherm Q cooling loop that we would install. And then there's also a 2 megawatt water glycol air cooling system to control the dome atmospheric temperature. There's also a lot of different penetrations into containment that would need to be made to make it compatible with this cooling architecture and electrical INC, things like that. And just to power the cooling system, you need a new substation right there at the site. So it's a small 2000 kVA transformer that would be located right there to step down the higher voltage. This would be a site where commercial fueled reactor demonstrations could be undertaken. So they're using things like high assay LEU. The reactor size will be limited to that Connex box size, kind of what you'd see on the back of a tractor trailer, 20 feet by 9.5 feet by 8 feet. And I've posted the link to our preconceptual design summary report that's available on OSDE.gov. If you just type in NRIC, it should be one of the first results on there. So the next facility that we've been working on is what we're calling the Enrique Lotus, the Laboratory for Operation and Testing in the US. So this would be modifications to the existing zipper cell at INL. And one of the things that we need to do there is create an equipment hatch either on the roof or coming through the side of the Lotus cell. But the baseline ended up being for the preconceptual design coming through the roof. It would also have similar heat rejection systems, but you would be limited to 500 kilowatts of thermal power with the closed loop, and then there's an additional 500 kilowatts of air cooling for the cell. This is a special facility. Zipper is a special facility because it allows the use of safeguards category 1 fuels. That means that you can make reactors on the order of 10 to 20 times smaller than what you could do with commercial fuels, but it can only be, these types of machines could only be demonstrated in a place like Zipper that has the special approvals needed for those types of fuels. Again, I posted the link to the summary report if anyone's interested in digging into the details of one lines and PFDs and isometrics. The next project I wanted to talk about is the molten salt thermophysical examination capability. So there's been a lot of interest in molten salt reactors in recent years. And one thing we realized when we first got started is that there's not a resource or a capability to do post-irradiation examination of molten salt reactor fuels. It's a different problem than doing PIE on solid fuels. And so this will be a modular hot cell installed in the FCF facility at MFC, and it creates a versatile workspace for industry or academia to look into these molten salt reactor fuels, you know, the thermal conductivity, the density changes as a function of temperature, any of the electrochemistry, heat capacity experiments that they want to conduct, and also gives us a place to synthesize small quantities of these fuels to do the equivalent of kind of fuel qualification for liquid molten salt fuels. And this would be, you know, a true first of a kind capability in the US. There is not an existing facility where you can do this kind of work. So we're really excited about this one. We think this opens up a new type of architecture for advanced reactor development. We're also applying what is called digital engineering on all of our projects here. And there's a lot of different definitions for, you know, what is digital engineering, but at the high level, it's management of requirements in a database rather than having paper documents that are requirements documents. So you've got, you know, this single source of truth where if a requirement changes, you don't have to go backdate all these other documents. It automatically is connected to all future documents and cascades through the database that way. It also lets us do some of the common things that we're using the systems engineering approach, like functional decomposition, configuration management, and we're actually using it for this process called model-based systems engineering, where you tease out the requirements for the system by building flow diagrams, and those functions end up translating back to functional requirements, but they also are connected in the database to the actual asset or component or system that's going to satisfy that requirement. So it really gives you a really nice, clean, organized way to do requirements verification and also translate preconceptual design type things into engineering documentation that's self-consistent. So another project we're working on is a collaboration with the Nuclear Energy Advanced Modeling and Simulation DOE program. This one is called the Virtual Test Bed. So you can think of this as NEAMS has all of these physics packages, capabilities to model all the different thermal hydraulics, neutronics, finite element analysis and materials, but they aren't necessarily integrated together in a application that can be used, that day by an industry reactor developer. Some of them have been done, but not all of them for the types of reactors that industry is interested in. And so using the Moose framework, which is kind of a big differential equation solver that enables you to plug in these NEAMS packages, we're putting together a database that has reference plants, design reference plants for these types of advanced reactors. So, whether you're working on a sodium fast reactor or a heat pipe microreactor, you'd be able to go in, download this reference plant model, and then start changing the parameters to target your design and do modeling and simulation with your design. But it really takes a lot of the front end work of integrating the model out of the developer's hands and short circuits that process. So this has been a really exciting thing to be a part of, and I think industry is really going to appreciate this as they start to use it and see how effective the tools are. So the last project I wanted to put on everyone's radar is this idea for the back end of the demonstrations, experimental reactors that we're planning going into the future. The waste and D&D component of any of these projects it's not the most exciting topic to bring up on the front end. Everyone's interested in what the reactor can do and what all the applications are, and how much clean, reliable, safe power it's going to produce. But we recognize that it's extremely important to understand what's going to happen on the backside of these demonstrations before you even get started. And so that's the vision for this DD Preconceptual Design project that we've just kicked off. It's set up so that we are going to enable timely and cost-effective execution of post-reactor operations for reactors that use the NRIC test beds I mentioned earlier. And we want to do that by establishing a decommissioning and deactivation capability to support the successful deployment of these experimental reactors and protect human health and the environment. So those are the main topics I wanted to hit. Happy to answer any questions or provide more information if folks are interested. Thank you. I guess now I will hand it over to Corey McDaniel.
Great, thank you, Nick. And Nick and I have done this kind of a big team a couple times before, talking about the reactors that NRIC is supporting, particularly with the experimental reactors and the reactor demos that INL supports, projects like the NuScale project that most of you are aware of, and probably saw the DOE announcement of the $1.4 billion support for that project. So with the Industry Engagement Office at INL, we handle those partnerships with the laboratory on the, I guess you'd say, the cell side from the INL. We on the procurement or supply chain per se, but the projects that we support, things like reactors working with NRIC and other reactor demonstrations. Those are some of the areas that industry engagement is involved with. So I think Nick did a pretty good job covering what's been going on recently with the DOE awards, the Advanced Reactor Demonstration Program. As he mentioned, 2 of those reactors, X Energy and TerraPower, received awards for demonstrations. We at INL remain in contact with those groups and have had discussions about the option of those reactors also, either in addition or in lieu of demonstrating those reactors in Idaho. We have a total of 9 ongoing discussions around site use permits to host any of these reactors at the INL. We are eager to hear the results of the risk reduction awards, as Nick mentioned, hopefully in the next week or so. Probably we're hearing no later than next week, we might hear those. So for some people, that will be a Christmas present. For INL, we partnered with 18 of the applicants, including almost all of the, I think all but one of the risk reduction applicants. So we expect that regardless of which companies are awarded those, it'll be 3 to 5 awards. We expect that several of those will be partnered with the INL. So we're looking forward to getting those agreements in place. And I mentioned site use permits. I said NuScale had received the first. Oklo has a site use permit, and we have 9 others in the pipeline. Some of those we hope to be able to announce in the very near future. Again, these are the first steps towards these reactors. So if you're following this from a supply chain perspective, it's not going to impact anything immediately. But most of these reactors are, the goal is to demonstrate and deploy by 2027, as early as 2027. Some of them will be around NuScale 2029. The Pele reactors, those could be even sooner. And some of the space reactor and space propulsion opportunities could also be sooner. We hope that they'll be sooner. So again, I'm open and available for any questions about how industry engagement works and supports NRIC and other opportunities to partner with the laboratory. I guess just to make it clear that we are the organization, we handle those industry engagements with partners who work with or utilize the INL, which may result in supply chain opportunities versus those. We do not handle procurement or any of the relationships on the buy side. That's Stacy's organization. And so I think with that, I was going to pass things over to Lee Nelson, and Lee can talk about, again, one of our capabilities that we're developing, the versatile test reactor. You're mostly aware that we have the advanced test reactor already in place, and the MFC, Materials Fuel Complex, where we do a lot of the work to support industry. And the VTR we're looking forward to as this is really the tool that allows us to support the advanced reactors, especially the fast reactor technologies that we've been supporting at the laboratory for decades. This will give us that tool that we think will give us the advantage over any other national laboratory in the world when we have that capability. So if unless there's any questions, Stacy, I don't know, I have to bow out around 10 o'clock. So unless you wanted to do Q&A right now, I will pass things over to Lee Nelson to talk about BTR, and I'm available until 10 for questions, or anybody, you can reach me offline if anybody has any questions about industry engagement. Lee, I'll pass things over to you now.
All right, thanks, Corey. My name is Lee Nelson. I work on a versatile test reactor project. I do have some slides to share. I don't see the share screen thing. Who can make that happen?
Eric, we'll give him just a second.
Okay.
Do you see it yet, Lee?
I do not.
Okay, hold on just a second. I'm opening up your slides. I'll share them from my end.
Okay, that'd be great.
I just got to get rid of some things here. Let me see what we can do here.
You know, technology is a wonderful thing when it works.
Well, I'm struggling as well.
Oh, there we go.
See if that worked, Lee. There you go.
Okay, so it looks like it's taking, let me get the right screen up.
I see your presentation.
Okay, is it
There
full
we go.
screen? Now it's on full screen. Okay, that's
Yes,
the one
sir.
I wanted.
Perfect.
Okay, thank
You're
you.
good to go.
So, thank you. As mentioned before, my name is Lee Nelson. I work on the Versatile Test Reactor project at INL. And today I wanted to give you a quick description of the project and then provide a status of where we're at, some of the accomplishments we've made to date, and where we're headed going forward. And then also wanted to discuss some of the local supplier needs that we anticipate. A lot of those will kick off over the course of the next year or so. And those supplier needs will be required whether or not the VTR is built in Idaho. The alternative site is the Oak Ridge National Laboratory in Tennessee. But whether the VTR is built here or in Oak Ridge, the same supplier needs do apply. And at the end of the presentation, I'll be talking about the draft environmental impact statement that we're currently working on, and we'll ask for some input from you all on that document and hope to have you participate in that process. So the VTR project kicked off in 2018 as a result of a number of studies that highlighted the need for a high neutron or high energy neutron test facility. At the time, there were no facilities within the United States that were available to perform that kind of work that really is needed to develop advanced nuclear energy systems. The only available facility currently is in Russia, and for many reasons, that capability is not as available to us as it once was. When the project was kicked off, Idaho National Laboratory was identified as the lead laboratory, and another 5 national labs were also identified as having capability and skills in sodium-cooled fast reactor technology, which was the preferred one that was identified through those studies. Since the project kicked off in 2018, we have since had a number of calls for universities to help us to define experiments that would go into the VTR, and those teams are currently working, have been working for the last 1.5 or 2 years. And we also have 10 industry partners currently that have capabilities in sodium-cooled fast reactor technology. The principal ones of the industry partners are those that are helping us with the conceptual design and initial supply chain studies, and those are General Electric Hitachi, TerraPower, and Bechtel National. The project is being managed under DOE Order 413.3b, which is the Department of Energy procedure on acquiring major systems. And it has a number of critical decisions, which currently we are working through. Now, just to give you a little bit of background on what the VTR is, it is a test reactor, only a test reactor, and it's used to develop advanced nuclear energy systems. Then the specifics are that we work on advanced materials, advanced fuels, also instrumentation and sensors that are needed for all those types of technologies that rely on fast neutrons. And the conceptual design of the versatile test reactor is a sodium-cooled pool type with a power level of 300 megawatts thermal. That is the power level that is needed to get the neutron flux required to do the testing. And you can think of this reactor as a larger and improved version of the experimental breeder reactor that was built at the Materials and Fuels Complex in the early 60s and operated until the mid-90s. And on this slide, you can see in the upper right-hand corner, there is a picture of our 3-dimensional representation of the reactor. And if I could just describe what each of the major pieces and parts are, the large boxes to the left of the red one are a series of sodium to air heat exchangers. Each of these heat exchangers rejects about 30 to 35 megawatts thermal of heat from the sodium that's generated in the reactor to the local environment, to the air. And when the reactor is running, these things, all 10 of these would be just rejecting about 30 megawatts thermal to the air. The next picture down on the right, you can see a cross-section of the reactor facility inside. And the large area that it's called the experiment hall up higher, and then down low below grade, you can see the grade on the outside of the facility. Below grade, you can see the reactor itself. The fast neutrons would be generated towards the bottom of that vessel. The dimensions on that vessel that's below grade are approximately 20 feet in diameter and 60 feet tall. And the experiments would be located about 40 feet down below the reactor top, the reactor head. That's where experiments would be inserted and subjected to that high neutron flux. That is the reason why this facility has such a tall ceiling. The ceiling is about 80 feet tall, and that accommodates the long string that's needed to put the experiment down into the reactor, and also the casks that are required to lift and to manipulate the experiment as it is placed into the reactor. During operations, hot sodium is generated from the nuclear reactions, and that exits the reactor vessel head at the top, and then the piping you can see takes that hot sodium out to the sodium to air heat exchangers, where it's rejected to the atmosphere, and then the cool sodium, after the heat has been rejected, come back in and re-enter that reactor vessel in the top. So that is more or less what the facility looks like. To do an experiment, a truck would come into the facility, the experiment would be taken off the truck, put into storage holes inside of this experiment hall. When they're ready to be placed in the experiment, a cask would be brought over, the experiment would be picked up, brought over to the top of the reactor vessel head, and then inserted into the reactor vessel. The facility would operate for a period of about 100 days, and then we'd have a 20-day refueling cycle and move the experiments around as needed, and then the reactor would start operations again. So we would have 3 operating cycles each year, separated by a 20-day outage for refueling, shuffling fuel, and shuffling experiments. Once again, this facility is used strictly for research and development. There's no power generated by the facility, no electrical power, and it would be authorized by the Department of Energy, as is currently done for HIFER at Oak Ridge and ATR at INL, and other treat at INL as well. The Department of Energy manages and authorizes several different reactor facilities, and this would be another one of those that is operated underneath the authorization of the Department of Energy. Of course, as we go through the licensing and licensing, so to speak, and authorization for operating this reactor for nuclear safety, the Nuclear Regulatory Commission will be observing, but they are not the authorizing agency. The Department of Energy is. And so this reactor is a unique capability, and many of you may be familiar with the Advanced Test Reactor, which is also operating on site at INL. That one produces low energy neutrons that have been moderated by water, because it is a water-cooled reactor. Since the VTR is a sodium-cooled reactor, we have fast neutrons, and those would be available for, once again, for the advanced nuclear reactor technology development interests within the U.S. So the milestones that we've achieved to date, our first major milestone that we achieved was in 2019, and that established the mission need for the versatile test reactor and identified the need for the U.S. to have a fast neutron energy spectrum capability, and directed and authorized the funding for it separately and within Congress. And this approach would fill a national security interest and also scientific community's needs for this testing capability. We most recently achieved Critical Decision 1, which was in September of 2020, and that milestone was associated with completing the conceptual design and the conceptual safety design of the facility. And this approval provided the cost and schedule ranges. And just for information, the cost of the plant is between $3 and $6 billion, and that includes constructing the facility, making the fuel, training up the operators, and putting the facility into production or into testing mode. And so all of those things were were completed with critical decision 1. The alternatives and then the analysis of alternatives identified the Idaho National Laboratory as the preferred option for siting of the VTR, with Oak Ridge National Laboratory as an alternative. And then for fabricating fuel, the Idaho National Laboratory was identified, as well as Savannah River, with not a preferred location identified for the fuel manufacturing. We are currently working on achieving critical decision 2-3, which we project to complete as early as 2022, but more realistically in the 2024 timeframe. And to achieve that milestone, there are a number of things that we need to do, primarily complete the preliminary and final design and the associated documented safety analysis work. Those 3 things would need to be completed. As part of that, we would identify those pieces of equipment that require more than just a few months to fabricate and bring on site, and we refer to those as long lead procurements. As a part of that effort, we would need to identify suppliers for some of that equipment, and I suppose that's why a number of you are interested in, this is where a number of you would be participating with the project, is some of those supplier qualifications, and then also with filling those long lead procurement needs. Once again, we expect to achieve that milestone in the 2022 to 2024 timeframe. The last major milestone would be critical decision 4, and we project to complete that in the 2026 to 2030 timeframe. And with the completion of that, the construction is done, operators have been hired and trained and can operate the plant. We verified the key performance parameters for the plant, and DOE has approved the documented safety analysis for the nuclear safety concerns for the VTR. And we would also have completed an operational readiness review, which demonstrates that we're ready to operate the plant. So that's where we've been. The critical decisions 0 and 1 we've completed, and then the critical decisions 2, 3, and 4 are yet to go. Now the supplier engagement, I've put a lot of words on this slide. I'm thinking that, I don't really want to read all these slides to you, or these lines to you, but at the same time would like to cover this information because I do think it'll be of interest to you. First off, we are currently negotiating an engineering, procurement, and construction contract, blanket master contract, with a team that is being led by Bechtel National, or B&I. Their main subcontractors include GE Hitachi and TerraPower. And this team is very similar to the one that Nick talked about earlier with the Advanced Reactor Demonstration Project. They are involved currently with both the VTR and with that ARDP call. Now, future procurement of goods and services, particularly those that might be supplied by local industry, would be performed by the Bechtel National contractor. We will be going through them for nearly all of the future materials and services that would be provided during preliminary, final design, and then during construction. And visited with Bechtel, and their plan is, and they typically do this, is they provide a website that's available once the preliminary design is well underway. And based on our current schedule and our funding projections, we anticipate to have that web link available by about a year from now, in the December 2021 timeframe. And you would go into that web link to get your name on the list, so to speak, as to be a potential supplier of goods and services. And we expect the procurements underneath this contract to be anywhere from commercial grade to fully compliant NQA1 equipment with things like N-stamped vessels. Our reactor vessel, for example, which contains a sodium, it's about 20 foot in diameter and 60 foot tall. And we would need that, expect that to require an N-stamp and able to be used in the VTR. And during these procurements, we would, of course, have a bias towards awarding work to small businesses, and we would have a goal for the amount of work that would be going to small businesses. That has not yet been established. We're still working on that. And then, of course, as the project progresses, you can see some of the local labor needs we might have, and also during operations, the type of people that we need to help us operate the plant. And we really do recognize the need for local suppliers. for making the VTR a success and look forward to working with you over the coming months and years to help make the VTR successful. Now I want to get into the National Environmental Policy Act. We've been working on the environmental impact statement for a little over a year now. We published a notice of intent last August and held a couple of public meetings last August as well. We have just barely finished up with preparing the draft EIS, and that will be sent out for public review here within the next couple of weeks. And the alternatives that will be showing up in that environmental impact statement is first, a no action alternative, which would keep things as the way they are currently. And then the alternatives are to either build the VTR in Idaho or in Oak Ridge, and then to build fuel either in Idaho or at the Savannah River site in South Carolina. And when that EIS goes public, it is highly desirable to have comments from especially the local communities involved. So I would ask you if you could download the EIS, look through it, and provide public comments. That would be greatly appreciated, very helpful. The department does consider public comments when we go through these EISs, and your positive comments especially would be most welcome. There's usually a 45-day comment period, which is sometimes extended to 60 days, and there'll be at least one public meeting over the web, just as we did last August. There'll be another one that describes the EIS, and a lot more project information will be available in that document. Then once we finish the draft EIS and receive public comments, we will work on resolving those. Expect to do that within a month or two, and then we would be publishing a final environmental impact statement followed up with the record of decision. Final environmental impact statement being produced in the spring time frame, and then the record of decision in the summer, this coming summer. And within the record of decision, we would identify whether the VTR is built in Idaho or Oak Ridge, and whether fuel is fabricated in Idaho or at the Savannah River site, or a combination of the two. So once again, would really appreciate your comments on that environmental impact statement when it comes out. Would appreciate your participation in that process. So in summary, when it becomes operational, the VTR would become the world's premier fast spectrum test reactor, and it would allow technology developers from around the world to come and test advanced nuclear energy systems and to prove the materials and fuel that are needed to make those safer, better, faster, cheaper reactors available to the marketplace. And VTR would provide that missing piece of research and development infrastructure that would be needed to perform that mission. And I would like to note that even early in the design phase where we are now, the VTR is making a positive impact. That ARDP call that TerraPower and GE has responded to, a lot of that was facilitated, and some of the concepts were developed during development, the conceptual design phase of the VTR. So we've already seen a positive development on the nuclear energy innovation within the U.S. The next thing I would like to mention is that the registration for local suppliers will be available about 1 year from today, and that would be done through Bechtel, through a Bechtel national webpage. I expect us to have a VTR website that would have a link to send you to the BNI webpage where you could register. And then lastly, the VTR will be authorized and operated under DOE authority, just like many other test reactors currently on the INL site. And that DOE authorization would be working closely with Nuclear Regulatory Commission, so that we're sure to meet all of the requirements within DOE, but at the same time make sure that we're being as safe as we possibly can as we go to operate this reactor. And that's all the information I have for today. And Stacy, I guess I turn it back over to you now for questions.
Yep, I should be back up there now. You should see me. Thanks, Lee, for doing that. Thanks to all of our presenters today. We do have a few questions that have come in. So Nick and Corey, if you want to bring your webcams back up, I'll go ahead and ask these questions. Nick, I think this first one's actually for you. Will these contracts require CMMC L3 compliance? And I don't know what that is, so.
As you know, I'm not an expert on CLL3 compliance. I think we are using the INL procurement functions as NRIC. So all of the RFPs and RFIs are going through the standard process there. Yes, I don't know, Corey, you're an expert on procurements, right? This is the wheelhouse for you, maybe.
Actually, Nick, I think in the background, that book, the third book down on the right, it says CMMC. I think you used to study that in college, right? Actually, I would defer to procurement on that. I'm also not an expert on CMMC.
Scott, you may want to reach out to me and I'll see if I can't do some more research on that and get you an answer on that question. So, what opportunities do NRIC and VTR have for non-nuclear focused companies? Nicholas, you jump in there first.
I think, nuclear engineering and the design and development of these plants, it involves so many different disciplines and companies. Not everything is a safety significant component that's got to have the N stamp that Lee was talking about. There's a lot of different construction and systems, services, things that are going to be needed to get these things accomplished that are not nuclear specific. They're, general construction and data management and things like that. So I guess which specific industry, because there's definitely some that probably aren't going to fit into a nuclear development project, but I wouldn't say that everything we're doing is going to revolve around, nuclear grade components and services that are traditionally thought of as nuclear companies.
Exactly right, Nick. Agree completely.
All righty. What are some of the biggest supply chain gaps you all anticipate for advanced nuclear technology?
I can take a swing at that one too. Component development for advanced reactor concepts is a big one. Depending on the coolant choice that reactor designers are working with, there's an existing supply chain for pumps, valves, heat exchangers for the light water fleet. We're pretty good at making steam out of water, and it's used in a lot of different types of processes. But when you start looking at these advanced coolants, helium, molten salts, liquid metals like sodium or lead, there's not an established supply chain there, and there are subtleties and wrinkles to designing those types of components that make them not something you can just grab off the shelf that works for a different process industry. I'll give you an example for molten salts and helium. Because you're trying to keep a low oxygen environment, that oxide layer on the top of metals is typically not there. So at high temperatures, you can get fusing of metal, like valve faces, or even things like doing a chain in a helium environment. The chain rubbing together will knock off that oxide layer and you get some metal fusing there. And so there's just special considerations for design of components in those working fluids. And that supply chain has definitely got to grow with the advanced reactor community.
Okay, let's see. We've got a lot of questions coming in. That's great. Thank you to the participants. The question, I think this one kind of goes back to me almost. What media platform will be used to notify potential suppliers that supplier quals and engagement? For the VTR, that, as Lee mentioned, BNI will have their supplier website up in about a year. For opportunities coming out of the Idaho National Laboratory, we'll be using our opportunities portal and have that information available there. One of the other questions I saw on here is, are they going to be posted through INL or through beta.sam.gov? And at this time, we've been doing some of the larger expression of interest on beta.sam.gov, but the procurements themselves will come out through INL and not on that federal platform. Here's a question. Is there any need for engineering services suppliers, example being engineering and drafting services rather than fabrication services?
Yes.
Yes.
Probably more limited for VTR, but yeah.
Okay.
So I can maybe add a little color commentary to that. We have a range of projects with NRIC. I mentioned the biggest ones on my presentation today, but some of these projects, they're not $10 million projects. They're smaller, non-nuclear. Like one of the ideas that we have that we're trying to get spun up right now is the design of a helium component test loop. So electrically heated, no nuclear components involved. And most of the time we like to take something through kind of that pre-conceptual design phase and then start working with an external engineering organization on the track towards fabrication. That ends up being an effective way to do things for us.
Okay, I skipped a question here. How does the MESTEC collaborate with the VTR?
How does who collaborate with the VTR?
Mystic, the molten salt thermophysical examination capability.
Oh, not a lot of interaction there right now, Nick. Not sure what else to say about that. Not a lot, if any.
So here's where I think there will be collaboration. Once VTR is running, there's a lot of fast spectrum molten salt designs that are going to be interested in testing in VTR. And so you can imagine an irradiation experiment being conducted in VTR where you've got that nice, hard, fast neutron fluence, and then the sample, the post-irradiation examination of that sample will be done inside the Mystic modular hot cell.
Okay, Nick, here's
we
another one.
We do have test loops that are under development for the VTR. The university team's working on the experiment requirements. There is a test loop that's under design. TerraPower is leading that effort, along with a couple of universities to develop the test loop so that molten salt experiments, the fuels and materials that we use in the reactor can be tested in the VTR. So I guess that is the interface, Nick. Good one.
Nick, this one's for you too. The Dome AE procurement is ongoing. Can you comment on when the Lotus and Mystic opportunities may be put out for bid, and what procurement opportunities do you foresee coming from the D&D planning effort?
Ooh, so the Lotus RFP should be coming out shortly after the Dome RFP wraps up. And then I'm not 100% sure on the status for the Mystic RFP. I know the procurement specification for the modular hot cell is almost complete. It might already be complete, but I don't think it has actually gone out for bid yet. The D&D effort is still pretty early, so I wouldn't expect anything on that until at least fourth quarter of this year, if not first quarter of 22, just because we've only been working that project for a month and a half now, 2 months. So we got a lot of work to do before we know what we're trying to buy.
Okay, here's a follow-on to the Dome project, Nick. Is the Irig Dome project a DOE line item? And if so, what are the critical decision points in the program?
That is a great question that I'm probably not equipped to answer. I stick mostly to the technology and engineering aspects, and Ashley Finan, the director, manages the financial and regulatory pieces. So I probably am not the right person to answer that one.
Okay, Lee, this one's for you. BNI is the EPC contractor, but long-term, will ongoing operational and experimental supply chain be managed from INL, DOE, or BNI?
Likely managed by, well, if it's built here in Idaho, it would be managed by INL once the construction is complete and we've entered into operations. That would be operated by INL. and all those procurement type activities would be done by INL.
Okay. And Lee, maybe explain this one a little bit. Are you competing with other national labs? I think this is for where VTR will be built. And what do you mean by competition?
Well, it's not really competition. DOE is currently, as part of the environmental impact statement, will be evaluating whether to build the VTR here in Idaho or to build it in Tennessee near the Oak Ridge National Laboratory. Once that decision is made, then we would progress at one of those two sites. Right now, the INL is identified as the preferred location, partly because of its remoteness, among other things, and some of the PIE facilities that are available. And Nick talked about some of the additional capabilities that other programs are bringing in there. In our view, that would be the ideal location to site it, but Oak Ridge is being considered. And once again, that decision gets made in summer 2021 with the publication of the record of decision.
Okay. What documentation technologies and standards do you use?
A lot.
A lot.
That's a long list. We have a code of record that we developed for the VTR, for example, that identifies all of those. Unfortunately, that's not available to people that aren't under contract with us. That's I wouldn't say business sensitive, but it's not widely available. But there's nothing out of the ordinary. It's the kind of codes and standards you would expect.
Yeah, I would say we try to leverage consensus codes and standards as often as applicable, and that ranges from, you know, the NQA1 standard down to the American Society of Welders and the inspection technique that you would use for, you know, a weld to make sure that it's leak tight. I mean, if someone would have told me that nuclear engineering was writing so many requirements, I wouldn't have believed them when I was back in school. It's a lot of requirements documentation.
It is, yeah. The SME, American Welding Society, all of those apply.
Here's another question. Is this thorium-based reactors? If so, is VTR securing resources?
A thorium-based reactor?
Mm-hmm.
No, we're not a thorium-based reactor. Our fuel is uranium, zirconium, plutonium alloy. And so, yeah, the thorium's not part of the VTR.
So there are thorium reactor concepts that are proposing to do demonstrations in the NRIC test beds. And, you know, you can't start a fuel cycle on thorium. You have to start with uranium and then you breed thorium into U-233. And so those are the kinds of machines that are, you know, looking at experimental demonstrations in Lotus right now.
All right, there's one more quick question that I want to ask, and then I'll wrap it up. A lot of these final questions I've kind of saved to the end. People are asking where they're going to be able to find our procurement needs and what the opportunities are. As I mentioned, for INL opportunities, those will be posted on the INL opportunities portal, and BNI will have its opportunities portal up and available in a year. So be looking for that. To follow up with that, if you have any specific questions, please reach out to me directly. My email is stacy.francis@inl.gov, and that's Stacy with a CEY and a Francis with a CIS. So you can reach out directly to me. I've posted that in several of the questions there, my email address. So reach out directly to me and I can forward your questions on to the project teams so that we can get you an answer back. We are out of time, and I apologize to those whose questions have gone unanswered. Again, reach out to me specifically and I can try and get you in touch with the appropriate technical people, because I am certainly not the one to talk about thorium-based reactors or helium test loops or any of those kind of things, but I do know where these guys reside, so I can forward those on to them. I want to do a quick plug for next month's supplier engagement webinar. We will be doing a 3-hour session. I know that that's a long time to sit in front of a computer screen. but we will be focusing on construction activities at the Idaho National Laboratory and how to get engaged in those construction activities. So we'll be showing a forecast of what we think upcoming construction needs are going to be. And then we'll talk about the safety requirements, what's required, your employee modification rate, and just overall how to engage in construction with the Idaho National Laboratory. So that will be on January 13th, I believe, at 9 o'clock. You can register for that on our webinar webpage. And then in February, our presentation is going to be on service contracting at the Idaho National Laboratory. So our procurement manager for service contracting will be doing the presentation specific to contracts within that area. So I think that that'll be a real good overview for companies who are interested in service contracting with the INL. So with that, again, I thank you to my presenters today for bringing this information to us. I thank those who were in attendance online. It was great to see so many people in attendance. And with that, I'm going to wish everybody a Merry Christmas and Happy Holidays. Stay healthy and safe. Thank you.
Thanks, Stacy. Goodbye.